In almost every introductory computer science course, you're taught the CAP theorem as a simple triangle: consistency, availability, and partition tolerance. The rule is simple: pick two and you must sacrifice the third. It's a clean, elegant mental model that fits perfectly on a whiteboard. But here is the problem. The CAP theorem, as commonly understood, is lying to you. In the real world, you don't actually get to pick two. This binary choice suggests that we can somehow opt out of network partitions, or that availability is a simple toggle switch. By treating these complex properties as a menu of options, we overlook the nuanced reality of how distributed systems actually fail and how they perform under pressure. Today, we're going to deconstruct the triangle and look at what's actually happening under the hood of your favorite databases. To understand why the triangle fails, we first need to be precise about what these terms actually mean. In the context of CAP, consistency doesn't need ACID consistency from the database world. It specifically means linearizability. Every read must return the most recent write, as if the system were a single node. Availability is also strictly defined. Every request to a non-failing node must result in a successful response, not just eventually, but immediately. And finally, partition tolerance means the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. When we use these strict definitions, we start to see the cracks. If you demand perfect consistency and perfect availability, you are essentially claiming that your network will never ever fail, which, as any SRE will tell you, is a dangerous assumption to build on. The biggest lie of the CAP triangle is the suggestion that you can choose CA, consistency and availability, without partition tolerance. In a distributed system, a partition is not a choice you make, it's a condition that happens to you. If your nodes are connected by a network, that network will eventually fail. Routers reboot, cables are cut, and congestion happens. When a partition occurs, you are forced into a choice. Do you stop accepting writes to remain consistent, or do you keep serving requests and risk divergence? Choosing CA is effectively saying, I will assume my network is perfect. But if the network fails, and it will, your CA system becomes neither consistent nor available. It simply crashes. Therefore, in the real world, you are always choosing between CP or AP during a failure. Partition tolerance is the price of admission for distributed systems, not a feature you can toggle off. Since partitions are rare but inevitable, what happens the other 99.9% of the time when the network is healthy? This is where CAP falls silent. Enter PACELC. It stands for, if there is a partition, choose between availability and consistency. Else, choose between latency and consistency. This else clause is critical. It acknowledges that even when everything is working perfectly, there is still a trade-off. If you want high consistency, every write must be replicated to multiple nodes before it's acknowledged. That takes time. That adds latency. If you want low latency, you might acknowledge the write on one node and replicate it in the background, risking a temporary inconsistency. PACELC forces us to realize that the trade-off isn't just about failures. It's about the speed of light and the fundamental cost of coordination. Another lie of CAP is that consistency is binary. In reality, consistency is a spectrum. On one far end, we have linearizability, the gold standard, where the system acts like a single source of truth. On the other end, we have eventual consistency, where nodes might disagree for a while, but eventually settle on the same value. But there's a whole world in between. Causal consistency ensures that related events appear in the correct order. Session consistency ensures a user always sees their own writes. By framing the choice as consistent or not, we ignore the specialized tools that allow us to tune our systems for specific needs. Modern databases like DynamoDB, Cassandra, or CosmosDB don't just ask you to pick C or A. They give you a slider to choose exactly how much consistency you're willing to pay for in terms of latency. Ultimately, the lying part of CAP is that it focuses on what is possible rather than what is practical. In a modern microservices architecture, the cost of C, strong consistency, is often coordination. Coordination requires chatter between services. Chatter requires network round trips,
Round trips mean your P99 latency starts to climb. Many high-scale systems actually choose AP not because they don't care about consistency, but because they can't afford the latency tax of coordination during normal operation. They've realized that for things like likes on a post or items in a shopping cart, the business cost of a temporary inconsistency is lower than the user experience cost of a slow interface. Engineering is about managing these costs, not just following a theoretical triangle.
So if CAP is a lie, what should we use instead? First, stop thinking in pick two. Instead, start thinking in trade-offs under failure. Ask yourself, what happens to my system when the network drops 5% of packets? Then think about PACELC. How much latency am I willing to tolerate for consistency when everything is normal? Distributed systems are messy, probabilistic, and full of gray areas. The CAP theorem was a brilliant starting point in 1998, but it was never meant to be the final word. By looking past the triangle, we can build systems that are more resilient, more performant, and more honest about the reality of the network. Thanks for watching, and stay curious.